Hello, I would like to welcome everyone to the 2021 International Conference on Communication and the workshop on emerging topics in 6G communications. My name is Yahuza Bello from the IoT Research Lab at Manhattan College. I will be presenting our work titled B5G Predictive Container Autoscaling for Cellular in bulk packet flow. I would like to thank you for your interest in our work, and I hope you enjoyed the presentation. As you can see from this slide, the content of the presentation is as follows. We first begin by explaining the motivations and contribution of our work. Secondly, we will move on to discuss the proposed auto-scaling container-based EPC implementation. Thirdly, we will discuss the proposed AWS load balancing technique, that is an optimal approach and a heuristic approach that we developed. Next, we will discuss the performance evaluation of the two proposed schemes, that is the auto-scaling container-based EPC implementation and the load balancing technique. And finally, end the presentation with concluding remarks. Several research studies in the literature propose adopting network function virtualization technologies to virtualize mobile core network entities and deploy them on virtual machine or cloud environments, such as AWS and Google Cloud platforms. This indeed solves the proprietary hardware dependency problems of these network entities, of these core network entities, and offers a better return on both capital and operational expenditures for mobile operators. Additionally, deployment of mobile core network components on the cloud will result in both high availability of network services and high scalability of the respective components that are being scaled. With this in mind, several proposals emerged in the literature on how to effectively scale these virtualized mobile core entities. Some research studies propose horizontal scaling, where we add or remove instances of a component, while others propose vertical scaling, where we add or reduce resources allocated to that component. For example, if you have a VM, you can add more CPU or more RAM to that VM. So one recent research work proposed a combined horizontal and vertical scaling mechanism for virtualized EPC. And the authors implemented their proposed scaling mechanism on AWS. Like all the other papers we surveyed, this paper also deploys the virtualized EPC on virtual machines and developed Python scripts for the scaling functionalities. Although this implementation is done on AWS, however, they did not leverage the services offered by AWS, such as the auto-scaling services and load balancing services. Additionally, hosting the EPC entities on virtual machine takes more time to instantiate while scaling horizontally, which is a big factor to consider. Whenever you have a very large network, which actually, as the number of UEs increases, you would like to add more components. So the time factor is going to increase exponentially. It is clear that utilizing the built-in services offered by AWS will not only make the scaling more efficient, but it will also reduce the overhead introduced by the additional models dedicated for the scaling mechanism. Therefore, the main contributors of this paper is twofold. First, we propose a predictive horizontal auto-scaling model for a container-based EPC that utilizes the embedded services offered by AWS, which will be explained in detail in the next slides. Second, we propose an optimal model and a heuristic algorithm for load balancing that aims to achieve maximum proportional fairness among instances on AWS while jointly maximizing the throughput achievable in the system. Now, let us talk about the proposed predictive auto-scaling model for the container-based EPC, which is shown in Figure 1. We can see from the figure, the proposed model is in two parts. We have the radio access network, which consists of the simulated UEs and E node B, and we have the core network part, which consists of the containerized version of the EPC entities. To leverage the services offered by AWS, we deploy the containerized EPC entities on AWS Elastic Container Service in a single container instance. This container instance is basically the EC2 instance, or you can say virtual machine, hosting a Docker runtime where all the containers are deployed. Utilizing the service model within the ECS, each containerized EPC entity has replicas attached to the embedded auto-scaling group at the ECS level. One interesting feature of the ECS service is that you can set the number of containers you want to run at all times. For example, you can set 3 MME containers to run at all times, and whenever one of the MME container is down for any reason, another one is automatically instantiated to replace it. Also, AWS offers several auto-scaling policies to trigger this scalability functionality. For example, there is target tracking, simple policy, step policy, and so on. In this work, we opt to go with the target tracking policy. The idea behind this policy is simple. All that is required is to set a threshold for the chosen metric. The metric can be either in terms of CPU utilization, memory utilization, or even a custom metrics that you design yourself. You can also see from the figure that we have an elastic load balancer that resides between the radio access network and the core network. The function of this load balancer is to forward the radio access network traffic to the MME container and the SP gateway U container according to the 3GPP standard. So when the auto-scaling policies are breached, horizontal scaling of these entities is triggered. Likewise, when the auto-scaling policies of the other container, that is the HSS Cassandra container and the SP gateway C container, are breached, their horizontal scaling, their auto-scaling, or their horizontal scaling will also be triggered automatically. In this slide, we begin to discuss the proposed optimal approach for load balancing. We formulated an optimization model that aims to achieve fairness in request assignment among instances and at the same time maximize throughput in terms of tasks or requests processed in a given time period. Equation 1 reflects the mathematical model of the optimization problem. As you can see from the table, Pi represents the assignment probability of instance I, U is the utility function that captures resource allocation according to the criteria of proportional fairness, N is the total number of requests, lambda I is the processor resource factor for instance I, and so on. So the idea is to achieve fairness among these instances, such that every instance can be assigned tasks or requests regardless of their computational resources, and at the same time have the overall maximum achievable throughput. Looking at the constraint, the first constraint given in equation 2 ensures that all the requests are assigned to the instances, and the second constraint given in 3 reflects the fact that an instance can either not be assigned any request or can be assigned the entire incoming request. It is clear that from the mathematical model, this problem is a nonlinear problem and can be easily transformed to a continuous problem by simply introducing a variable. For instance, we opt to go with ether, which is given by Ni over N. So the transform constraint after putting the value of ether is given in equation 5 and equation 6. So after this modification, the optimization model becomes a linear convex function in ether, and simple solvers such as CVX can be used to obtain an optimal solution. So this slide presents the heuristic algorithm, which try to assign a request to the instances based on their processing resources and the number of previously assigned requests. The idea behind this approach is simple. Each instance will have an assignment factor lambda, which is proportional to the instance processing resources and inversely proportional to the number of assigned tasks to this instance as shown in equation 7. So the main idea here is each time the load balancer receives a request, it will assign it to the instance with the highest assignment factor, and then it updates it for that instance and continue for the next, and continue the same thing in the next iteration until all the requests are processed. So this part of the presentation is dedicated for the performance evaluation. So first, we implemented our proposed auto-scaling model for the container-based EPC on AWS. And to evaluate its scaling capability, we consider three metrics: the number of attached process completed for UEs, that is a complete successful UE attach and connection process, the CPU usage of the container of the containerized EPC entities, and the RAM usage of the containerized EPC entities as well. As you can see, the table in this slide presents the allocated resources and the configuration setting of our implementation. For example, the MMU container is allocated 10 gigabytes of storage, 1 CPU of core, 1 gigabyte of RAM, and for the configuration settings, 1 MMU container is deployed in configuration 1, and 2 MMU containers are deployed in configuration 2. An important thing to notice is the auto-scaling threshold. Is that the auto-scaling threshold is set at 90% of the CPU utilization in each entity. And as you can see, we allocate a lot of storage to the simulated RAM for CPU and 16 RAM. This is because we are actually, just for the simulated RAM to be fast, that's where we allocate more resources to it, because we are not actually testing the simulated RAM. In this slide, we present the simulation results of the three metrics. Figure 2 shows the results obtained for the number of completed attached process, which is given in terms of registration per second for 64 UEs. It can be deduced from the figure that with configuration 2, that is 2 MMU containers handling the attached process, more UEs are being attached successfully, and the auto-scaling policy was not violated, and thus scaling is not triggered. And for figure 3 shows the RAM utilization metric for the two configurations. And you can see that the RAM usage do not saturate as the workload varies for 64 UEs. Next, we tested the CPU utilization of the EPC entities and found that only the MMU container provides a significant change in terms of the CPU metric with maximum of 64 UEs. So we evaluate only the CPU utilization of the MMU entities as shown in figure 4. It can be deduced that configuration 1 was able to handle at most 56 UEs without violating the auto-scaling policy threshold, which, if you remember, I stated earlier, it was set as 90% of CPU utilization. So, and as the number of the UE increases beyond 56, the auto-scaling policy is violated, which triggers a horizontal scaling of the MMU container to serve the additional UEs added to the network. In contrast, looking at configuration 2, configuration 2 was actually able to serve all the 64 UEs without violating the threshold. If you look at the 64 UEs, I think the CPU installation is about 72%. So it's still not 90. So the whole of the configuration 2 does not require any scaling. For the load balancing, we evaluated our proposed optimal and heuristic approach with the well-known round-robin algorithm for task scheduling and assignment. Figure 5 shows the objective function versus the number of iterations for the three algorithms. It can be noticed that the optimal solution converged in the first few iterations and achieved a better objective function value than the other two algorithms. And still, the proposed iteration algorithm outperformed the round-robin. Next, to ensure that the optimal formulation has converged to an optimal solution, we compare it along with the heuristic and the round-robin with the exhaustive search algorithm, as depicted in figure 5. It can be seen that the exhaustive search has converged to the same solution as the optimal, which proves the optimality of our optimal solution with respect to the objective function. To conclude, in this paper, we presented a predictive auto-scaling model for containerized APC. We implemented the model on AWS and evaluated it in terms of the number of attached process completed by UEs, the CPU usage, and RAM usage for all the containerized APCs. The simulation results revealed that MME is the most critical entity that requires scaling as the workload varies when the auto-scaling threshold is set to 90% of CPU utilization. Moreover, We formulated an optimization model that aims to achieve fairness in request assignment among instances and at the same time maximize throughput in terms of tasks and request processed at a given period in time. We verify its convergence with simulation results and show its superiority over the heuristic and the round-robin algorithm. These are some of the references that we use in the paper. So this is the end of my presentation, and we appreciate your time and attention and hope to see you again in future conferences.